Saludos. Sorry I'm really late. Everything crashed. Nothing was connecting. And so I had to start late. I want to spend today doing the review I promised for calculus and for statistics, because for chapters 3 and 4 you need calculus. Well, calculus and statistics will inform your understanding of the material. Can you hear me all right? If something happens in that the video, if the video freezes, you remember, if it's blurry, refresh the screen. If the things I'm saying don't correspond to the video, I might have lost a connection. I have to restore the connection, so let me know in the chat or text me, okay? Because sometimes I get carried away talking and I don't notice. So I sent you 2 documents. Hopefully you can view them as I'm speaking. Obviously you can't do that if you're on a phone, unless you print them. Anyway, I'm not sure about your situation, but at any rate, this will be recorded and you can review it later, right? Hi everyone. Okay, so I have this, I just want to get started because I'm starting so late. I've prepared this handout, and at the top I give you some links. Okay, so I'm using my new iPad. That's another variable right now. This will be the first time, so I'll be getting used to this. Okay, so this here is a video with review exercises if you really want to practice calculus. I will just show you the essentials for understanding this course, but if you want to go deeper, you can go into it. Okay, so this is mathematics. I actually am going to share a video with you that you can review. We'll watch it together today. Okay, so I made those tiny URL links to make it easier to find. Or at least to search for them. It's easier to type in. All right. So who's here? We have 13 people. There's almost 30 people in the class. So of the people who are here, what is a derivative? Can you tell me in the chat? Hello? So here's the question. La razón del cambio, the rate of change. Okay. What does that mean? What does that mean in terms of mathematics? What does that mean in terms of statistics? Anyone? What is a derivative? It's the rate of change. Maybe you guys understand that. So most of you, 14 of you, don't know how to express in any other way what a derivative is. Okay, so that's good. That's good because now we're going to talk about it. I'm gonna show this video and then we're going to discuss it, okay? Give me a moment to set it up. Sorry, I have to do these. I have to fit this here. I could probably do it like this, easier. No, then I lose my control. All right, so let's watch it here, like this. Watching another video instead of live stream. Let's see what happens. Okay.
And we want to find a way to tell how much the...
Okay. Everybody ready? Here goes.
So, we have an equation, and we want to find a way to tell how much the equation is changing at a given point. So how do we accomplish this? Well, we know the change in a line is simply the slope of that line. So how about we start there? The equation for the...
It's not playing for you. It's very interesting. I gotta refresh. You can hear it, but you don't see it, right? Let me do that again. Interesting. I'm gonna do that again. You can hear, but you can't see it. Oh, maybe I'm supposed to press it different. One more time. If this doesn't work, I'm just going to explain it, and then you guys can watch the video on your own. Just like the way he does the animations. One more time.
slope of the line is the difference between 2 points on that line. The point...
Very strange. Very strange. I can't do this. That's so funny. I'm trying to think. Wow, if I use the YouTube app. Not sure what you mean, Mario. Anyways, so I'm gonna put the sound down. Wow, it's so weird. It doesn't show. Can you hear me now? Is that better? What a tragedy that this doesn't work. Well, back to my derivative. Okay, so what it is, I'm just gonna have to do it myself, is the slope of a line at a point. That's what a derivative is. The slope of a curve, sorry, at a point. So if you have a curve, and you want to know the slope of the curve right here, the derivative is that, okay? So if this is the x, presuming you understand the x and y axis, so this is like the function, and this is the x-axis, right? Then this is at a value, at any value x. This is the y-axis, or f of x. So this is f of x. That's the function. And the slope of this curve, the red curve at the point marked at the value of x, here, is a matter of taking 2 points and calculating the change in y over the change in x, right? That's the slope. Well, we call y the function f of x, the change in fx over the change in x. Everybody's fine with that, right? So we take 2 points, we can use this one here, that would be x and f of x, right? If I call that x and f of x, and one that's further away. So that's a second point. So this second point would be a distance away, so it's going to be a little bit more than x, right? It's going to be x plus h. The h is just some distance away. And so that's the horizontal coordinate, and then this will be the y coordinate, the vertical coordinate. So that's the point here. And that other one is where we want the slope. Okay, so we want the slope here. So what we do is we say we're going to calculate the slope So we're gonna, okay, that looked really messy. Let me do that again. I want to erase. So this is like the change in y, and this is the change in x, correct? So the change in y would be this one here minus this one here, which is change in y. And on the bottom, the change in x would be this one minus this one. What's x plus h minus x equal to? What's x plus h minus h? I mean, x plus h minus x. Very good. Somebody's answering my questions. If you don't answer it in the chat, that's okay, but at least ask yourself. So that's just h. So see, this is the change in x. So what we're going to do is take the change in y over the change in x, and let them become closer and closer and closer. And that's what the animation of the video does. It just shows that we make that distance between these 2 points smaller and smaller and smaller. That's what this says, limit. So when you take calculus, anyone who's taken calculus, you spend a lot of time on solving limit expressions like this. Not a lot of time, but you take some time to solve limit problems like this to find the derivative. But I'm not going to ask you to do that. I just want you to understand that that's what this symbol means. The symbol that we write f prime x is the first derivative of the function with respect to x. Now the slope, note it, that the slope here is at a point, this point. So you'd actually have to punch you have to put the x value in there. So we're gonna, I'm gonna show you simplifications so that I don't have to do it this way. But essentially it is the slope at a point on a curve. We can also write the derivative with this expression. Okay, that says the derivative of the function with respect to x so that's repeated here on the top. So you're going to hear me say that a lot. So I'm not, like I said, I'm not going to use the limit function. Oh, you're going to see my notifications. I have to turn all of them off. We're not going to use this limit function. We're just going to keep in mind that's what a derivative is. It's the slope of a curve at a point. So From here, there are simplifications that are derived, or rules of derivatives that are very handy. Very useful. First of all, let me ask you this question. I'm going to erase this noise. And refer you to this video here. At any point, take screenshot because I might change the view, okay? I don't like a messy screen. Okay, so what if your function is a line? Here's a function of a line. Let's say that's accurate drawing. So what is the derivative let me do that again. The question so find the derivative at x equals 6. What's the derivative at x equals 6? Let's say this was 6. What's the slope? What's the slope at that point for this curve? I could also call this f of x, right? So what's the slope? Claudius is 3. X equals 6. When x equals 6, y is equal to, okay, my drawing's really off, but anyway, don't worry about that too much. My scale is different. When x equals 6, y equals 3. I need to turn off my notifications. I think you're seeing those. Or let me say f of x. So x equals 6, f of 6 is 3. So that's what 3 is. So this is the point 6, comma, 3. My question was, what's the derivative? Okay, go back to what is the derivative. What's the definition of derivative? Put it all together, synthesize this. I have to go and turn off my notifications. Think about it. Anybody, come on. What is a derivative? I have a new device, so I have to do all the settings. I didn't do them all. Okay, nobody knows. This is blowing your mind. Find the derivative at x equals 6. The derivative is the slope of the curve. What is the slope of the curve for this function? The slope of a line is always the same. All the way up, all along the line, the slope is always the same. What is the slope of this? Maybe I won't use the word. I'll just say slope of a line is always the same all along the line. It's always, in this case, what is the slope? It's always a half. So let's see. What is the equation of a line, just to take a step back if you don't know what that is? So the equation of a line always looks like this. A plus bx. In our case, we didn't have an a, we just had a bx, where b is the slope. And A is called the intercept. We can do another one. I'll put it in. Okay, so that's what we have. In our example, we had this function. Okay, this function only has a slope. So the slope is, people are getting it, it's 1/2, right? Oh, I just erased my, oh my goodness. I'm looking for that highlighter. I'll just use this one. Okay, so this is the slope here. So the derivative of this function is the slope of the function at a point, but it's always the same no matter what the point is. So it's always going to be the b. So there's a summary for you. So we write the derivative of the function f prime x is 0 plus b, which equals b. What is this 0 plus b? What happened? Well, let's go back a step. What about a constant function? What's a constant function? A constant function is a function I don't really like this palette. All right. I'll have to get used to this. So a constant function, this is a constant function. F of x equals 4. That's a constant function. It's always 4. No matter what x is, y or f of x is always 4. What's the slope of this function? F of x equals 4. Let's put it again at 6. Say this is 6. All right, so this is the point, 6, 4. What's the slope of that function at 6? Manuel says it's 0. There is no slope, right? Yeah, there's no slope. This function has no slope. There's no inclination. Slope would have to be like this or like this. This is a positive slope. And this is a negative slope. So far, we know what the derivative of a constant function is. The derivative of a constant function is always 0. So any constant function for instance, fx equals 4 or fx equals a, as written here, the derivative f prime x is always 0 because a is constant. Now we go a step up. So if this is a flat line with no slope. When we go to a line with a slope or linear function, this is a constant is a special case of linear function. That's one way to say it. When you take the derivative of a function with a slope, the answer is it's just a slope. So now you know how to take the derivative of two functions, constant and linear functions. Questions? So you notice here I use the fact that a is a constant and the derivative of a by itself is just 0 because of what we said above about constant functions. They have no slope. So what we're going to do is use these properties, these rules, to compute derivative, and there's just a few rules. There's really not a lot. You're not going to spend your class computing derivatives. This is just so you can read the textbook, okay, and understand what it's telling you. So that number in a line, so we talked about linear functions last class. We had a linear function but with many dimensions. Okay, this is just with 2 dimensions. These are just 2-dimensional. But I can put it in many dimensions by adding more variables, and you still use the same approach. However, you always have to be concerned with respect to x. What variable are you taking the derivative with respect to? Okay, so here we're just in 1 dimension. We're always with respect to x. But last class we talked about income being a variable, so we would have to take derivative with respect to income. alone, keeping all the other variables constant. That's the terminology. So whenever you're doing economics and interpreting results or interpreting demand curves or supply curves, you're using calculus results, okay? So you're using it, you might as well understand it, where it's coming from. All right, so recapping. The derivative of a constant is always 0. Derivative of a line is always the slope of the line. Always meaning for all x. I should add that. If it's unclear. No matter what x is. Okay, what about a power function? So we're going to go, so what we're doing is we're going up by degree. Well, let me stop on the linear function for a second. Let me stop on the linear function from last class. I'm going to get rid of the red. I'm going to use blue. So we made so you have a function like quantity demanded equals A plus B price plus C income plus D, let's just put one more, related good price. Let's say the other ones are negligible. And I ask you, oh, now using Q again, that's not good. So I'll just say, what is the derivative of the demand curve now notice I have to say with respect to what, right? So what is the derivative of QD with respect to income? Remember, this was price, this was income, and this is related price, related good price. So so why is it C? Like before I just told you it's the thing in front. But now what we're doing is we're going to treat all of these you're going to treat this as a constant, and you're going to treat this as a constant. It's not a variable, it's going to be set, it's going to be a number. So like I would have to find the P, certain P, and plug it in, and certain PR and plug it in, and so it's at a certain value, it's set. But M remains variable, the income remains variable. So of course, when I take the derivative, I can write, I'm going to use the prime, or I'm going to write the notation for you so you can see it. Right, with the squirrely D, we do this curly D for the partial derivative with respect to M, all else constant. This is what it means. Or all ceteris paribus, all other variables are held constant. So that's what the idea of the constant is. So this just becomes, notice, because of the rules, this is a constant, so this becomes 0. This is a constant, so this becomes 0. This is a constant, so this becomes 0. All that's left is Cm. So that's why this is just C. So in doing that problem, I've used rule for a constant function, and I use a linear function rule. The constant function rule made these go to 0 because I treated them as constants, and that they have to go to 0 when I take the derivative. And then because this is the slope, it's the term in front of the variable, it becomes C. Any questions? Okay. So most of that's it. That's what you need to understand. It's the slope. Derivative is the slope of the curve at a point. So it gives us it's a slope, right? So we interpret it as change in y, like we would change in y over change in x. But in this case, we say it's change in QD for change in M. And usually we say for one, because we imagine there's you can imagine there's a 1 under here, right? Because C or C over 1, those are the same thing. So for an additional, for 1 unit change in M, how much does quantity change? Okay, oh, you can't see that, so bear with me, I'm going to make it visible. There. So one additional dollar of income, QD changes by C. Quantity demanded changes by C. Okay, so this is a marginal effect for one additional unit. It's very messy looking, isn't it? Margin. I'm going to try and spell that a little neater. All right. So it happens on the margin, we say. It occurs on the margin. One more unit. What happens to QD? All right, so what if we go up a degree? We have a function of a higher power. Right now, with a linear function, and remembering this is just a linear function in several dimensions. This is the linear function in 2, 4, right? Four dimensions, but we don't draw that. We usually just talk about the quantity demanded and the price on 2 dimensions, and we see the other variables affecting a shift in the curve. Okay, but let's see. If we go to a higher function, higher order function, that's what we're going to do next. So the next rule, with the next rule you have most of this covered for the course. I'm going to erase this. Ready for the erase? Yeah, so just take a screenshot so I can continue. And then you can decide if you want to keep those screenshots or throw them away, because you get it, or you write them into your notes. All right, so let's see an example of a power function. Here's my function. Y equals x squared plus 3x plus 2. So I'm not going to draw this on a coordinate axis, but this is a parabola. This will be like this, something like that, right? I know it's going up just because of what I know about parabolas. If I was to draw it, it would look like that. So now this function has many derivatives, many slopes. How many slopes does this function have? Can you hear me all right? I'm giving you a chance to respond. I have a few questions. So how many slopes does this function have? Are the slopes positive or negative? Does it have a zero slope? Anybody else want to respond before I give you the answer? Okay, so how many slopes does this function have? Well, there's a slope here. Well, I have to make this, I'm going to make this bigger first, and I'm going to draw this for you. What just happened? No. Something locked. Okay, do that again. I don't know why it does that. What's the best way? Okay, so there's a slope here. There's a slope, sensitive screen. Okay, there's a slope there. There's a slope there. There's a slope there. There's a slope there. The answer is infinitely many. Okay? And like, because this curve goes on forever. This curve goes on forever, right? This is a function that goes all the way left and right. So there's infinitely many. Does everybody understand that the slopes will be infinitely many as well? So there's infinitely many points in here, right? If you think of it's a continuous function, so there's infinitely many positions, points along this curve. I can't even draw them all. I'd be here my whole lifetime writing all the points along here. So who understands that answer? Infinitely many. I would have to tell you which one I want specifically. So now that I said that, what's the answer to the next question? Okay, so what's the answer to the next question? Right. There's positive, there's negative, there's positive, negative, and a zero slope, I should say, and a zero slope. And it depends on the point, depends where I am. If I'm here, okay, so at this one, what is the derivative here? Is that positive or negative? What about this one? Is that a positive or negative slope? So this is negative slope. What about here? Is this positive or negative? Okay, Gerardo's getting it. Everybody else? Come on, guys. So that's a negative slope, and all of these are negative when what is happening to the function? If this function defined your sales, let's say this was a function of sales. Whoa. So say this is a function of dollar sales. When I talk about money, you know, when I don't understand things, I put it in terms of money I understand better. So I'm putting it in terms of money. Right, declining, right? So when the function is declining or decreasing, you see negative slopes. When the sales are increasing, or the sales are increasing, you have positive slopes. Now what's in between? Yes, Mario, that's right. So what's in between negative and positive slopes? Right. Right between them is, even though my function is a little bit off, is this, where there's, I'm going to use this color. It flattens out. This is a zero slope. And the zero slope is the worst you can do in sales. And that's really important. If this is a function of sales. I'm trying to let the point hit home. So you want to know about that, right? Now hopefully your function of sales is not going to look like this, but anyway, I just tried to make the point. Could look like this. Depending what X you're using. Okay. So my point here is that this is the worst, right? And you want to know the worst, and you want to know the best as well. So if I inverted this and made this going down, we could talk about the best sales, optimal sales. And we would want to know about that too. Okay, so now you get this. You got this, right? So when there's a curve, you have infinite slopes. That's why you have to say the slope at what point. That's why we need to get the derivative, we need to know what point we're interested in. But roughly speaking, when a function is declining, it has negative slopes. When it's increasing, you have positive slopes, and there could be the worst case or the best case scenario where the slope is zero. So let's get the function of the slopes. That's what we're basically going to do. We're going to find the function of the slopes. Let's find the derivative. So I'm going to rewrite this as well, no, I'll leave it with y because I use a lot of the f prime. I can just write y prime. So what is y prime? What is the function of slopes? The rule tells us, so we don't have to do a limit function solution for this. I'm not interested in that. There's a rule that says if you want, it's called the power function here. The power function rule. So when you have an exponent, the derivative reduces the power by 1. Does that make sense? Okay, so I'm skipping over proving this with the derivative formula and the limit approach. But what I am going to say, you see this, the n comes down in front and you reduce the power by 1. So let's use the example of a line. What if y equals two plus 3x? Well, I already know the answer. Y prime is equal to 3 because we discussed it already. No matter what the x is. Now you see why I have to write this as f of x. I'm going to rewrite this as f of x. If I write 2 plus 3x and then f prime x, I can write that as well, is equal to 3 for all x. So I can write it either way. Okay, those are the same thing. And to get this result is what we used before. I used this rule here and this rule here. Now I want you to do the same thing but use the new rule. How do we use the new rule? Okay, let's rewrite it. I'm going to write it as fx equals 2 plus 3x. And now I'm going to put an exponent here. It's just a 1, right? There's just one power. We don't write it because it's obviously power 1. But if I use the power rule, I'm going to get the same answer. Using the power rule, so this is an exponent 1, it's not a prime. So if I use the power rule, well, the 2 just becomes 0 because of the constant rule. Now this one, I'm going to bring the exponent down and reduce this power by 1. That's what the rule says. The rule says bring the exponent down in front and then reduce the power by 1. Everybody with me? So the answer is, if x is to the power 0, x to the power of 0 just ends up being 1. So that's why this is just 3 times 1 times another 1. So what happens when I bring the exponent in front is this multiplies by what's already there. Oh, that's confusing because that's an x. Let's see. I'm going to use brackets. So that's what happens. The 1 comes down, it multiplies to the 3, and then you have x to the 0. But this reduces to give you your final answer. F of x is equal to 3. Let's think about that for a minute. This becomes a 1. Oh, and I forgot my prime. So you believe me? So either you memorize or understand this rule, or you have to do it the long way. And I prefer to use these rules, which are derived from general theories that, well, I guess what it was done is the limit function was taken with this functional form, and it's proven that that's what the derivative is, okay? So I don't expect you to do that. I just want you to learn the rules. So let's use this rule with the function that we just discussed. How would I find the derivative of this function up here? So I'm going to rewrite it. I'm going to erase this stuff. Erase not all of this. Can I move this? Oh my goodness. No. No. I'll rewrite it. X squared plus 3x plus 2. So that was the function. I'm going to write it with f of x because just to emphasize that there's still different values of x. If I take the derivative, the rule, the power rule says take the 2 in front and reduce the power by 1. I could even think of that here, but we know that this is a linear function or linear portion. This will just be 3x reduced the power by 1 is 0. If I see this as a 1, exponent 1. And then this one just becomes 0 because it's a constant. So simplifying this is the result, 2x plus 3. Okay, so you can either use the power rule all the way through or use the other two rules that I told you about. The power rule is the more general rule for all of functions with powers. So notice this is a function. So that's why there are infinitely many derivatives or slopes. When x is positive, the slope is when x is negative, the slope is you're going to fill that in for me. When x is, the slope is 0. Give me the 3 responses in the chat. Okay, so when x is positive, the slope is positive. So this is a function of all the slopes, so if I put a positive in here, f of x will be positive. When I put a negative in there, what happens? So if I put a negative in here, how will you figure this out? Because sometimes it depends what negative I put in. If I put negative, if I put -1, it'll still be positive, right? So I think you should answer this first. Answer this question first. When is this slope 0? Solve it. You'll see that we'll be doing this. So when is the derivative 0? Do you follow the algebra? I can plug that in. Okay, so when x is -3/2 or 1.5, -1.5, the slope will be 0. So this between I'm going to have to write it a different way so it's clear. When x is between -1.5 to 0, or to infinity really, f of x is actually positive. Anything else, it will be negative. Okay, so just to make a point, this splits up into two parts. When x is -3/2 to infinity, fx is positive. When x is less than, more negative than -3/2, fx, f prime x is negative. So in other words, you can't see that. So let me put this so you can see it. So the slopes are positive up until -3/2, and then the slopes become negative. So that's like a splitting point. So if I draw this again, if I sketch this, I should be specific. It's a sketch. I don't want to draw the coordinates axis because I don't want to cross it the wrong way, but so if I did it like that, this would be where x, I have to erase this because I don't know if this is, no. This would be where x equals -3/2. That's the point I'm making, okay? So here it's all positive and increasing. And then here is decreasing. Slopes are positive when it's increasing. Slopes are negative when it's decreasing. So these are important points for what we're going to be doing in the future chapters. So in fact, your slopes are decreasing up until -3/2, and they're increasing after that. Okay? So, whatever you learned in high school math before calculus, realize you can use calculus to draw these curves as well. Okay, so there's my page. Now there's some other functions here, other rules, but really those are the main rules that you need to know. Sorry, I'm making you nauseous watching. Move this around. Okay, so I asked you a bunch of questions about that function. All right, let me give you a couple of problems and then I'll explain the other rules. And they'll come up later. I'm not going to focus on those. I don't really expect you to memorize those, right? You can keep this formula sheet with you all the time, but it is handy. So there's a bunch more rules on the other pages, and this is really where we're heading. The last page. So, on the last page, suppose you have a differentiable function. Then, as I've described, x generates a maximum or a minimum value of the function if it satisfies f prime x equals 0. That's actually what we just did. Okay? I asked you when is the slope 0, and we solved it for a simple problem. So since the first derivative is the slope of the function, this rule gives us the candidates for maximum or minimum. So if you have a function and you take its first derivative, either, if you didn't draw it and you just took the function and took the derivative, if you set it to 0 and solved, either what you found is a point where the function is a maximum or a point where the function is a minimum. Now, if you didn't draw it, you wouldn't know which one it was. So another thing to notice is what's called the second derivative. If the function is concave down, this is called a concave function. it will be the case that the second derivative will be negative. So I always think of an unhappy face or a frown, and I say that's negative. That's how I remember. Okay, so if somebody's unhappy, they're negative. If someone's happy, it's positive. Let me draw this with, let me draw the symbol outside. All right? So that's how you remember. The second derivative, if it's negative, what you found at the point, what you found is a maximum. If the second derivative is a positive, then you have a convex curve. And what you found was a minimum. And that's all the page says, okay? So you need these rules. I will say this again. This will come up again, but that's how, without drawing the functions, we'll know what we got. We take a second derivative. So let's go back to our problem and take a second derivative and confirm that we have a minimum. Let's do that. If you're still with me. Okay, let's go back here and take the second derivative of the thing in the box. Okay, so I'm going to erase this here and here. Okay, I'll leave all that. So what's the second derivative? So just take this one and do this one more time. The second derivative, 2x plus 3 is just a line, right? So the first derivative just becomes a line. So you see how we're going down in powers. We went from a curve, you went from a curve to a line, and then right now we're going to end up with a point. These are like degrees, you know, going from a point to a line to a curve. We're going backwards. From a curve to a line. And now you're going to see when I take the derivative, this is just 2. Since this is a positive, according to the rules I outlined on the last page, that means that for whatever x, there's no x in here, right? There's no x, it's just 2. So it's always positive. That means the result The zero slope is found at a global minimum. Have I lost you guys? I hope not. But that's basically it. I mean, that's the overview of what you need this for. Sure, there's different different exercises or examples, but that's what we're going to use. Let me look at the rules. Let me go through just a few of these to point some things out to you. But that's it, really. Once you have the power function, you can solve all derivatives, second derivatives. You can do third derivatives if you want, but we don't use those in this class. Should I give you another example? I might give you another example. So just to conclude, we drew this picture and we said we know that there was that f prime x equals 0 at x equals -3/2. And then we say that that's where the slope was 0 of the derivative function. And then we see that this is a positive second derivative. So it means that the value here is the lowest of all values for the function. It's a global minimum for the function f of x, for sales in this case. Okay, okay, good questions, thank you. Okay, how did I get 2? Okay, I took the derivative of this function. I take the second derivative, it means take this function here and do the derivative again. So the derivative of 2x plus 3 is just using like the line rule, so it just becomes its slope. It's 2. Is that okay, Gerardo? So 2 is positive. Doesn't matter what x is, it's always going to be a positive. Maybe I should give you some more examples. Do you get it? Do you see that? So I'm taking the derivative of a derivative. Oops. Sorry. All right, let's see. Gerardo, tell me you understood, or I'm gonna wait to hear. Okay, let me clear this. I'm going to clear all this out. So what I asked you to do was take the derivative of this. So you need to take the derivative of this thing. So what's the derivative of 2x? What? This is just a line. So what's the derivative of a line? So you forgot what we did at the beginning. What's the derivative of a line? A line that looks like that, what's the derivative? Any rule. What's the derivative of a line? You don't have to use the power rule when you have a line. You can just say the slope is 2, because the slope is 2. If you want to use the power rule, it's slower. So let's do that. If I start with you use that as a 1, x 0 plus 0 equals 2. It's the same thing. The question is, what's the derivative? It's a line, so the derivative of a line is always 2. So maybe I taught you a lot of things just now, but I don't want you to forget any of it. The derivative of a constant is 0. The derivative of a line is the slope. The derivative of a power function, there you have the rule. So the second derivative is 2. Well, the thing is, it should be synthesizing. We're going from a curve, the derivative of this curve, there's infinitely many, but it has a formula. The formula for all of them is just a line. So the curve reduces to a line. Oops. And then the line reduces to a point. So we went from a curve to a line to a point, and taking the derivatives, the first and the second. So because it's positive, 2 is a positive number, it just confirms what we already know, or just it's another way of identifying that when we found f prime x equals 0, we solved for when the derivative would be 0, and we found that x negative 3/2 was where the derivative was 0. So then we know the drawing, it's an easy drawing, but there's more complex functions than this one. So I know that that's x, that's where x equals negative 3/2. But it's a property also that the function, or the result is a minimum when the second derivative is positive. So that's what tells me that this is a minimum. It's the lowest point of the function. Okay, thank you for the questions. All right, so we have some other rules here. There's the sum. So if you have two functions added together, that's kind of what we're doing, because I had a 3x and a 2, or a 2x and a 3. It's like two functions. The derivative of the sum of two functions is just the sum of their derivatives. That's fine. We can accept that. That's logical. And the difference of two functions has a derivative. That's the difference of the two derivatives. So as long as it's always with respect to x, that works. Everybody okay with these two? At least 5 people tell me you're okay with these two. And be honest. You're going to be okay with those rules. Mario was asking me questions about the last thing. Okay, let me go back for an instant. It turns out in this problem that I gave you that the second derivative is exactly 2. Now the second derivative doesn't have to be exactly a number. It could be a whole function. You would have to plug in and see if it's a positive or negative. In this case, there's only one. There's only 2. We could just get 2. So it means the function is always a second derivative that's positive, no matter what. So that's how we know at x equals negative 3/2 we have. So what's the minimum value? When x equals negative 3/2, what is this lowest point? Let's make a point. Let's solve that before I continue. Completely finish this problem off. So if this is sales, what are your lowest sales? So you have to go back to the original function and plug that in. I'm plugging it into the original function. What do you get? Can't see. Trying to just turn this. I'll just make it bigger. So this is like negative 1.5. So if you can say this is millions of dollars to make it seem... How many millions of dollars? Yeah, I got 2, Gerardo, 2. So 1.5 negative squared plus bracket 3 times 1.5 negative plus 2. I get 0.25. So this is 1.5 squared is 2.25 plus or minus. So it's lost sales. And in millions of dollars, that would be $250,000. So that's the worst. So you need to be clear about what's the function, what's the derivative, what's the second derivative, and how to use them all. They all should be calculated at a particular point. Okay, so anybody else get my result? So there's only one minimum. I call it a global minimum because there's only one. Now, different function can have, if you have a polynomial function and the function goes like this or something, then there's many minimums and maximums, right? But this would be the global minimum, and this would be the global maximum. That's not our function shape, but that's why we make the... Very good, Gerardo. So that's why we make that's why we distinguish between, because see this one, what would we call this one? So these are all positions, these are all places where your slope will be 0. The first derivative will be 0. Here, 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 and here. But they all have different names. What's this one? What should I call it? It's not a global, it's a maximum, but it's not global. This is the overall maximum of the whole function I've drawn. This one here. This one here would be called the local maximum. Similarly, this would be called a local minimum. All right, you obviously, if you're talking about maximizing overall, you want to be at the global. And if it's cost, if you have a cost equation, you want to minimize overall, you want the global minimum. So that's why you need to differentiate between the two. And you would have to find where the function is doing these things. So you would find this, the first derivative, to find where the zeros happen, where these red marks are on my drawing. And then use the second derivative. So anyway, we'll get into that more later, but the point is that you can use the first derivative to find where the slope is 0 and solve it. You can either draw it or you can check all of them to see which one is the highest or which one is the lowest, just like I did here. Okay, you plug it in. Is that okay? Now there was only this one, there was only one place in our problem, so we found the result. It's it was negative 0.25. Negative, if we talk about millions of dollars, this is negative $250,000. Okay, so this is like an overview. Again, I'm not going to go so deep. We're just going to use these as tools. The derivative first to find where the slope is 0, and the second to confirm if it's a positive or a negative. In this case, so if it's a positive, you found a minimum. If the second derivative is negative, you found a maximum. You would have to plug in the value where you found the derivative was 0, and then you can determine what you have. If you have many places where the derivative is 0, like over here that I'm describing, then you'd have to check them all. Okay? All right, let's get back. Take a screenshot. I'm going to move. So, when I take the derivative of two functions that are added, it's just a matter of taking the derivative of each of them and adding them together. And we get that because that's what we were doing above anyways, right? Up here with the linear function, this is like two functions, a constant function and a line. You can think of it like that, or and we took the derivative of each of them, or we saw it as a line, either way, to get the answer. So similarly, if you have two functions added, you can just take the derivatives and add those. If you have two functions that are subtracted, you can take their derivatives and subtract those. Same, gives you the right answer. So that's, I think, straightforward. There are two more rules that I don't think we're going to use much, but let me just point them out, and then let's get into, I'm going to give some practice problem, and then we're going to go into the techniques of chapter 3, the technical exercises in chapter, I think it's chapter 3. Okay. So the product rule is a little different. It says if you have two functions being multiplied by each other, so this is one function and another function, to find their derivative, I don't know what beeped. To find their derivative, you have to take the functions, the first one's derivative, and multiply it by the second, plus the second multiplied by the derivative of the second one. Did I say that right? You have to take the derivative of the first one times the second, and then the first one without the derivative times the derivative of the second one. That, anyway, what it says there. So, I give you an example. I'm going to take this example. So this is, let me make it bigger. I'm going to make it bigger. So the rule says these are two different functions being multiplied as one. So what you can do, we know what the derivative of this is. This is just a line. And this is a parabola. But they're being multiplied, so who knows what that will look like. Let's just use the derivative rule. We're going to take the derivative of the first one times the second one as is. So I use the prime here to remind you. And then I take the first one and now times the derivative of the second one. So let's do the derivative. So what's the derivative of 2x plus 3? You can use the power rule if you want, or remember, this is a line, so what is the derivative of a line? Mario, good. 2. Perfect. And then we leave this one alone. Done. Now we're using, this is the rule, okay? So I had to use this new rule to do this, but inside of it is the old rules. So I'm mixing these things together. So this one I just rewrite. I do nothing here. Now what's the derivative of x to the power 2 minus 1? So now you have to use the power rule. So it turns a curve into a line. What is the result? So the power rule says, remember the power rule says, I can't show it at the same time. Go look at your notes. Yes. So it says that I need to take the 2 in front. I take the 2 in front and I reduce 2 by 1. And this constant just becomes a 0 because of the first rule. Or also from the power rule, you can see that that's 0. So the result is 2 times x with the power 1, and that's it. So the power rule turns a curve or a parabola into a line. You're going 1 degree down. So that's fine. I'm happy with that. Like, this is not, I don't need you to simplify this anymore. I just wanted to show you how to get the result. You could multiply that through if you really wanted to, and this was bothering you, and you could write 2x squared plus minus 2 plus 4x squared plus 6x, and then put these together. I'm not asking you to do that right now, but I'm just going to show you can do that. Simplify it a bit. So you're going to put the common terms together. Those go together. So this function, this first derivative becomes a parabola. Does everybody see that? So group together your common terms. Did I make any mistakes? You guys are doing good in the chat. I appreciate your comments. You're doing well. All right, so we learned first derivative, second derivative, what they're used for, and so far the power rule is going to get us most of the answers. This is just this is called the product rule when you have two functions being multiplied. An alternative thing you could do is you could just FOIL this out, like you could multiply this through and then just apply the power rule throughout it. You didn't have to do it with two functions. You know what I mean? You could have done this by like multiplying all of this out. What do they call FOIL or distribute? This times this, and this times this, and this times this, and this times this. And you get a new function, or a spread out function, and you should get the same answer. In other words, you don't have to use this rule. It does simplify things. If I was to do that, say I did that. Let me do that for you here. So this would become 2x to the power 3 minus 2x plus 3x squared minus 3. Does everybody see that? I think I can just leave it like that because they're all different terms. So 2x cubed minus 2x plus 3x squared minus 3. Now, take the derivative of that and see that you get the same answer. What do you get? Let's ignore what we did before. use the power rule. So this comes down and multiplies to 2. So this becomes 6x, and then you reduce the 3 by 1. And then minus 2 plus 6x. Did we get the same answer? Did I do something wrong? Did I do anything wrong? No? Make sure I didn't make a mistake. Why'd I have a minus 2 and a minus there? Did I miss something here? Oh yeah, I just didn't put a plus here. I transcribed it wrong. This is a plus. There you go, fix that. And now I have the same answer. All right, so what I just showed you is that you can avoid the power rule. I mean the product rule. You don't even have to use it. You could just distribute and use the power rule. So the power rule is the most powerful of all of them. It'll get you the answer. Is everybody okay with my correction? I just it was this one. It was a positive and I made it a negative when I was transcribing. So this is the derivative here. And I have the same result whether I do it this way by distributing, multiplying this to this, and this to that, and then here to here, and this. That's what gave me this. And then I took the derivative. So I just prepared it first. Okay. Really? We're probably never going to use the quotient rule. I can't think of when. But anyway, we get some practice with our derivatives. So let's do this. So the quotient rule says if you want the derivative of a function divided by a function. So here's my example. Here's one function divided by another. And you don't know how to draw it. And you want to find a maximum or a minimum or whatever's going on. You can take the derivative and set it to 0. So this is what we need to practice. Let's find the derivative of this. Well, this is hard to simplify to make it, one polynomial all on the same, not being divided. This is hard to divide into this, right? So we need an extra rule. So this is the rule that was developed using the limit approach that was above. The rule is that you take the derivative of the top, multiply it by the bottom function, then subtract the top function times the derivative of the bottom, and then divide by the bottom squared. Crazy, right? But it works. So let's practice following this rule. So we're going to use this, apply this rule. We're going to apply this rule to the function that I give as an example. So this is the top. Yeah, I'll do this in color coding. Let's see, yellow. So the top is yellow. This is the derivative of the top. Does everybody agree? Remember, the top is just a line, linear function, so the derivative of the line is the slope, so that makes sense. Then the rule says multiply by the bottom function. So we have to just leave it fixed, we don't change it, we just put it here. Now, subtract the top function, so I'm just recopying the top function. And then multiply by the derivative of the bottom function. So what's the derivative of this bottom function? So this is a parabola because it has a square on it. What's the derivative of that? So you see, it's always the same thing. Mario, you're good. You just forgot the x. Okay, 2x, right? Because remember, a curve, a line, and a point. So we went from a curvy squared function. It becomes, the derivative of that becomes a line. Because it's infinitely many lines. A curve is infinitely many lines. So the derivative of that curve is a line. And then the bottom squared, so I squared. And that's all I do, I don't do anything else. So, from this, all you really need is the power rule, remembering that derivative is the slope of a curve at a point, and I don't believe I'll ever have you use quotient rule. I don't remember it coming up. Maybe in one of the proofs. But in that case, I mean, I'm not going to expect you to do it. I'm just going to expect you to be able to follow along as I do it and where it comes from. All right? So I'm going to shrink this. And that's it for that. Questions about the quotient rule and what I did just now? I just follow along with this pattern. The pattern of the rule. Yes, I think it's a nice review for some people. This is all you need from calculus. And for people who've never taken it before, if you feel uncomfortable, it's okay. I'll repeat this when it comes up, and you'll have this to reference. Anyways, so Okay, so now, let's see if there's anything. These are some more rules here. Is the chain rule that you might see, you will see. The logarithmic rule, the exponential function rule. So when they come up, I'll refer to you to here. Right now, I'm just going to leave it, but you can review them. For people who've seen this before, people who haven't, just recognize the pattern and what's going on. This chain rule is for a function inside of a function. Now notice, this is a function inside of a function. Do you see that? You have a function in the bracket and then to the power 2. So that's a function inside of a function. The rule says take the derivative of the outside function and just treat the inside, don't touch it, don't touch the inside, just take the derivative of the outside function and then multiply it to the derivative of the inside function. So that's what's happening here. It's just treating this function as like a power rule, as though this is the power rule. It takes the 2 down, it leaves the inside to the power 1, and then it multiplies by the derivative of the inside, 2x. That's called the chain rule. That's a powerful rule too. Again, if it comes up, I'll reference this. You don't have to memorize this. It's helpful. But that's the chain rule. A logarithmic function has a derivative. This is the rule. And anyway, I don't know if I'm gonna get this. These are just the rules. If you learn the rule, you see the pattern. Okay. Pretty sure we won't see the trigonometric ones. But anyway, there they are. So you can reference this. If you see any derivatives happening, you can reference this, but I'm not gonna go through that. And then I talked about this briefly. All right, so I've done this handout. This is a reference for you, okay? And I'll go back to it. Oops. What I want to do. Oh, it's okay. It's time. Okay, it's 8:45. So what I need to do for you is then do the. Well, this is what I've done with the calculus is going to be helpful for chapters. Let me confirm it's chapter 3. Just give me a minute and I'll let you go. Right. in chapter 3, where the mathematical appendix. So this is all useful for the marginal analysis for optimal decisions. And the discussion in the mathematical appendix and the mathematical exercises. So we don't have any time right now, but I'm gonna do it, okay? I'm gonna continue. If you want to stay on, you can stay on. If you have to go, you can go. But I'm gonna continue on this video, conducting the this mathematical appendix on page. Well, I'll just at the end of chapter 3. Okay, so end of chapter 3, mathematical appendix and mathematical exercises. Are handled using calculus. So they're the results really of marginal analysis in the mathematical appendix, and then some exercises to practice what you learn. And then later in the course, I do have questions in the, I have questions in Connect that will expect you to be able to do this. So I know I'm giving you some time to do the reviews and or to do the remedial background stuff so you can easily or better read the chapters. Chapter 4 is all statistics, so you need a statistics review. I sent you a review, but you probably want a spoken review. So I will prepare that for you as well. Okay? So I'm going to continue. I'm going to do the theory of unconstrained maximization. And if you have to go, you guys can go. You can just say goodbye for now. I'll just continue. All right. Okay, we begin. I'm going to Start on a new page. Okay, we start with a single variable problem in its most general form. And we begin with an activity. The level of that activity is denoted as X. This activity generates both benefits and costs. So I'm trying to make this as general as possible, or the text does. The benefit function will be written as that, and the cost function benefit function could be sales, it could be positive, anything positive. And the cost function speaks for itself. The objective is to maximize the net benefit. So net benefit would be benefit minus cost. Now, when will it be a maximum? So let's take from our discussion, our earlier discussion. It'll be a maximum when the first derivative is 0, where the first derivative is 0. So since they're both functions of x, I could write it as where the net benefit, the first derivative, is 0. Or I write it as, you can see the notation, right, with a d, with respect to, we say, with respect to x. The derivative of bx with respect to x minus the derivative of cx, which is the cost, with respect to x, and that has to be 0. Well, when will that happen? This will happen at the x x star where marginal benefit, that's what this means, is equal to marginal cost. Precisely where one more unit adding one more unit of x such that the benefit, the change in benefit and the change in cost is identical. Now this is unconstrained maximization. So this is just without any other considerations of restrictions on how much you can, how much of the level of activity, any limiting factors. So let me do an example so you can see this in action. So this is unconstrained optimization. Yes. So let's take an example. Let's say, I'm going to give you two equations and then you're going to tell me what the answer is, because you guys will appreciate it or be able to understand better if you try it yourself first. So let's say the benefit function is equal to ax minus bx squared and the cost function is equal to cx minus dx plus ex cubed. Find the optimum. I want want you to find the optimum. I want you to find both X star that optimizes and the net benefit of X star. Let me give you, if you're here, well, it's only 5 of you, but you guys can try that. Give you a minute to lay that out. People who are watching can pause and try it themselves. Did I miss something? CX minus DX squared, sorry. So lay it out. So net benefit would be the benefit minus the cost. So it would be AX minus BX squared minus CX minus DX squared plus EX cubed. And this is A minus CX minus B plus DX squared minus E. B. Does everybody see that? And then we would have to take the derivative of that and set it to 0 and solve. Yeah, this has to be a minus in here. This is a minus. Can I fix it? So what I did was put these together. I put these together. So I grouped my terms, right? Because when I take the derivative, yeah. Okay. And then that's it. So when I take the derivative, that's going to matter. So let's take the derivative. I can use a prime, but I'll use the notation d dx is equal to, so in front of the x, this number just stays the same. In front of the x squared, the 2 comes down, and this stays the same. And in front of the x cubed, the 3 comes down, and this goes down 1. So this was the power rule that I used, where I treated these constants in front like constants. So this looks really messy. Oh, I'm off the screen. This looks really messy. Without numbers, because what I need to do next is set this equal to 0 and solve it. It's not going to be very nice. But you know what? I won't make you do this one. I won't make you do this one. But that's what you would have to do. Now solve. So the steps would be to solve this for x and let it be x star. And then plug the result back into the function to find what your net benefit would be. All right? So let's just do one. Let's do one of the problems in the mathematical problems so we can actually get a result. So mathematical exercise number 1. Okay, so exercise number 1. So the benefit function to the choice variable is x, so that's the level of activity you get to choose. The total benefit function is and the cost function is so 2 parabolas. The first question is, what is the marginal benefit, or what are the marginal benefit and marginal cost functions? the marginal benefit function, you can put a prime on it. Because there's only one variable, it's clear, right? I can just put a prime because I know the only unknown is x, and that's my choice variable. So I have here a parabola. I can use the power function throughout it, or I can see this as a linear function, and this is a parabola. So basically, the rule says the line becomes a constant. So this is just 170, or you could say the x power goes down to 0, if you want to think of it like that. And then here it becomes 2x to the power 1. So it's just 170 minus 2x. And the marginal cost function is, well, the constant becomes a 0, the line just becomes its slope, and here you apply the power rule. So I'm doing it both ways. So this is just 0 minus 10 plus 2 times 2 times x to the power 1, which is 10 minus 4x. So those are the two functions, the marginal benefit and the marginal cost. Part B is set up the net benefit equation or function and then determine the level of x that maximizes net benefit. Net benefit is equal to the benefit minus the cost. And we know that the optimum from what we did before I want to put the x. Where the first derivative of net benefit is 0, that's where the optimum lies. And we know that is also where the benefit is equal to the cost. So either we can subtract the marginal benefit by the marginal cost and set it to 0, or just set them equal to each other. So I'm going to set these equations equal to each other and solve for x. That's where my solution, my optimum is. Did I do my signs backwards up here? My goodness, what happened? This is, I don't know, I did something dyslexic right there. So that would be the answer there. No, what happened? Okay. This is minus 10 plus 4x. It's 170 minus. Okay, so that makes that minus 10 plus 4x. Oh, what happened? All right, so solving this for x, collect your terms. 170 plus 10 on that side, and 4x plus 6, I'm jumping again, plus 2x on that side. So I moved this over there and this over here. So that 180 is equal to 6x. So that means that x star, to solve this, x star must equal 30 units. So that's the optimum level of activity. And now if you plug that into the function overall, for the third question, so this is the best you can do in net benefit. This is the result. This third part is find what is the maximum level of net benefit. So net benefit, you remember, is benefit minus cost, the two functions. So it's 170x minus x squared minus 100 minus 10x plus 2x squared. So what I have to do is now, for all the x, use the 30. Put 30 in there. So this would be 170, 30 minus 30 squared minus brackets 100 minus 10 times 30 plus 230 squared. That's all you do? What do you get? Anybody there to calculate? You got something, Gerardo? Very good. Let's see. Anybody else? That's what I get, 2,600. So, well, we don't know if these are dollars, but this is 2,600 units. So that's the maximum level. It's not a question in the technical or mathematical exercises, but let's make sure that this is the maximum. How would we do that? You take the second derivative of this function and make sure it's positive. and you plug in, take the function, you actually plug in that value to make sure that it's positive. So let's take the second derivative. We only did the first one. Actually, we didn't even do the first one. We just set those two to each other. We set the marginal benefit and marginal cost equal to each other because we know that that's going to give us the solution. But let's take the first and second derivatives and prove that we have a maximum. So a maximum will happen if the function goes like that, if the net benefit function is concave like that, then you have one maximum. So let's check. The first derivative would be let me just write the function out. 170x minus x squared minus 100 minus 10x plus 2x squared. Then the first derivative would be 170 minus 2x. Well, maybe I should expand this before I continue. Let's do that. Let me just distribute this because it's going to get messy otherwise. So I'm just going to rewrite this as that and leave it like that. I won't even collect my terms. Well, I could. Let's just do that. We'll collect the terms. Oh my goodness. Okay, so let's write that. So the net benefit function, putting together the x's and the x squares. Let me know if I make any mistakes. It's minus? No. No. Yes. Minus 3x squared, which makes sense because a parabola that's concave will have a negative in front. So that makes sense. And then you have 180x, and then you have minus 100. I'm going to double check that. Sorry, 180x. And it's not minus, it's plus. What am I doing? See, that's what I mean. I think I'm getting tired. So 180x minus 100, there you go. Oh yeah, I forgot to mention, yeah, I'm extending it till next week. Don't worry about 3 and 4. Okay, so we're ready now. The first derivative is going to be minus 6x plus 180, which is what we had before, right? When we solved and we set this to 0 and all that, we solved with that. The second derivative will be negative 6. You see? The second derivative will be negative 6. What did I tell you? when the second derivative is negative, you get a maximum. So that's just confirming our result is a maximum. Okay, so it's 9:30. I wanted to do that exercise. I guess the constrained optimization, I should do it, shouldn't I? In the mathematical exercises, the first problem is for a total benefit. The second one, a similar problem but more complex function. And then the third one is about using, calculating a maximum but using a cost constraint. So that's constrained optimization. I should do that before we go. I also should mention if there's two activities you have to choose from, what you do. So when you have two choice variables, what does this look like? So this could be in production, you have to consider both labor and capital inputs, for instance, and you want to optimize profits or at least with, benefits to costs, or profits, in other words. So in general, net benefit would be a function of two variables. And we would write it like this. And you can do it with more than 2 as well. But because we have 2, we have to take each one in turn. So that means we have to calculate the partial derivative. So we have to say, if we were to take the derivative, we use the curly one, and we say take the derivative of benefit, of net benefit, first with respect to x, and then with respect to y. And I have to do the same thing for the functions that comprise the net benefit function. So I would have to do that for here, the benefits with respect to x, minus the partial derivative of cost with respect to x. And then for the y, I take the partial derivative of benefit with respect to y minus the partial derivative of cost with respect to y. And what you have to do is set them simultaneously to 0. That would give you the optimum. So you have to take those equations, set them both to 0, and solve. What this ends up showing you is in both cases, you would solve for the optimum x star, is found where the partial of benefit is equal to the marginal utility of cost. Marginal benefit is equal to marginal cost. And y star is found same way. The marginal benefit with respect to y is equal to the marginal cost with respect to y. Of course, this is going to be easier if you see the problems. So should we do one? I don't know if I have one here. Yes, I do. So let's do this without, I'm going to make one up. Let's make one up. Well, I'm going to borrow the question number 3 part, but okay, so for example, let's say the benefit function was like that. And the cost function I'm going to write it as b of xy and say the cost function was like that. So we can find x star and y star. So what I have to do is take the derivative for x star. I want to find the derivative of this function with respect to x and this one with respect to x and make them equal each other. So solve where the marginal benefit is equal to the marginal cost with respect to x. I guess I'm jumping. So okay, let's go up here and see what's the derivative of this function with respect to x. There's an x here and there's an x here. There's the y here is just at the end is just treated like a constant. So you treat y as a constant. Okay? So that leaves you with 3 plus y. That's it. Think about it. So now y is like a number 3 or something. It's just a constant. It's like a 4 or a 2. Okay, let's look at this function now. With respect to x, that just leaves, and where y is just a constant, that leaves 2. Oh, darn, this is what happens when you make up a question. So there is no way that I'm going to find x star because it disappears. 3 plus, I have to make up a different function to make this work. Okay, I'm going to change this. Oh my goodness. So I'm going to change this to a 2 and now it'll work. It will work. Okay, let's go back. Let's take the derivative of the benefit function. So this will now be not 3, but 6x. So the derivative of this with respect to x is 6x. This one is just, leaves the y behind. And then this one is 0. I'm going to do that again down here because I have a feeling you're not going to get it. So the partial derivative means, so I'm gonna put in red how you should think about this. So this could be like 3x squared plus 2x plus 2. So I made the y a 2, just like a constant. So that's why it becomes, using the power rule, 6x plus just the 2. But the 2 is, I made it, y. Anyway, if that helps. And then this is just 0, because a constant becomes 0. All right. So the cost function with respect to x is just 2. So this is one result in 2 variables. And now let's get y star. How will we find y star? So we have to simultaneously solve these problems. Y star is where the marginal benefit with respect to y is equal to the marginal cost with respect to y. And what will that be? The marginal benefit with respect to y will be, what we have to do now is just treat y as a variable and x as a constant. So that's for that part. And then we treat y as a variable for the cost and x as a constant. How did I do that? Let's go through it. So the partial with respect to y you can see my, okay, so the partial with respect to y, this is all just a constant. So this I don't even, this just becomes 0. This one, the y is the variable, so that, you can think of the power rule, that line just becomes the constant x, and then this y just becomes 1. You can also think of the power rule if that helps you. Okay? And the derivative with respect to y for c is just the 1. So what we get are 2 equations which I simultaneously will solve to find x and y. So when I wrote x star is found where both of those are true. You have to solve these simultaneously. Which amounts to I'll write it. I can't see it all. Solve together simultaneously. So this is going to be easy because here this changes to, okay, I'm going to move this up a bit. So this one just becomes x equals 0, doesn't it? So 0 activity, 0 of x. So if this is an input to production, you don't use any x. That would solve this one very easily. And then I should simplify that to x equals 2. So automatically one of the solutions falls out. So then I can substitute that into there because they have to be solved simultaneously. And what does that give? Unfortunately, a strange answer because I made this up. So that would be the optimum, whatever that means. So I just did this mathematically, but in the context of the problem, you would have to interpret that. So those would give you the optimum. None of activity 0 and negative 10 of activity. What did I say? None of activity X and negative 10 of activity Y. Then you would plug that back in. Then you plug that back in to get the net benefit. If that's what you're interested in. So we're solving for optimum, in this case for 2 variables at a time, 2 choice variables. Just going to double check my work. Any questions? Anybody there? Audio, your question? Wasn't the 0 y star? Not sure what you mean. So what I did was I did the partial equation for I don't know. I was able to erase that. Okay, so I do the 2 partial equations. I don't know. why I separated them. I don't have to separate them. To find both of them simultaneously, I solve the partial for x and the partials for y. And then solve the equation simultaneously. Okay, so look that over. So what if I wanted to find what the net benefit would be of doing this? So you would have to take this function and plug in x and y. Since x star is 0, this is going to be a weird solution. So x star is 0, so this becomes 0, this becomes 0, this becomes 0. It simplifies it a lot. And with a benefit and a cost function like this, the best you can do is break even, because this is not apparently great. So if you put 10 in here for y, minus 10, the net benefit works out to be 0. Again, I just grab these functions to make a problem so you can work out. I shouldn't have made it up. I always regret making up questions. So that's going to be, just to clarify, that will be minus 10. So the net benefit turns out to be 0, which is the best, because I guess any other combination will give you a negative if we figured this out. Or anyway, that's just doing the math. These are not good equations. No, negative 10 times negative times negative 10 is actually a positive 10. So this is unconstrained optimization. Let's do a constrained one. And then we'll go. We're going to keep going here. That's right, Gerardo. All right, so I'm going to do, oh, you can't see my math again. Okay, so I'm going to do unconstrained. So now I have to teach you, sorry, constrained optimization. So that's the case where you have a cost and a benefit function, but then you have a constraint. So the example will be question number 3. So question number 3 in the mathematical exercises a decision maker wishes to maximize the total benefit subject to a cost constraint. So notice, I could write this one as benefit of x and y. I mean, it's a function of x and y. And the cost constraint is written as, it's a line, in fact, okay? So to do this, to solve this, I introduce the concept of the Lagrangian multiplier. So I'm going to do this example. I'm not going to go through the theory. I'm just going to show you how you apply the theory. And you can read the theory. In the process, I'm showing you how the theory works. So what you do is set up the Lagrangian function to be maximized. So we use the big L and we write the benefit function plus, this is a letter lambda, Greek letter lambda, known as the Lagrangian multiplier. Oh. I'm going to put the function right in there. No, actually, no, I'll put the notation. I'll put the notation. So this is the Lagrangian function. This is known as the Lagrangian multiplier. And notice the form of the constraint, the cost constraint. We see the number in front of the x as the price per unit of x, and we see the number in front of the y as the price per unit of y, okay? And the total cost, so the total cost, the most we can spend is 70. So in our problem, if we set this up with the numbers I gave you, the Lagrangian multiplier will be 3x plus xy plus y plus lambda I need to put a bracket there. I need to either put a bracket here or a negative there. I'm going to, just so it can be seen clearly, I'm going to put brackets like that, okay? So I should be able to write this as 70 minus 4x minus 2y All right, so now this is the Lagrangian function, and what I'm going to do is just like we did before, just the problem above, where there's so many variables here, right? There's a x, there are choice variables x and y, and then the Lagrangian multiplier also acts like a variable. So what we're going to do is take 3 partial derivatives and set them all to 0 and simultaneously solve them. So we're going to take the derivative of the Lagrangian with respect to x, the partial derivative with respect to y, and with respect to lambda. So for the first one, we treat x as the variable, and I write 3, and again, x is the variable, so that becomes y. This y becomes 0 because x is the variable. Lambda stays, the only one, this becomes a 0, this becomes a 4, and this becomes a 0. And I can simplify over here that this is 3 plus y plus or minus 4 lambda, and I set that to 0. Now I do the same, now I do the partial derivative with respect to y. The first term has no y in it, so that becomes 0. The second term, there's a y, so it leaves x. There's just a y, so it becomes 1. Rewriting that, the first term has no y, becomes a 0. The second term, no y, becomes a 0, because it's just like a constant. And the last term becomes a 2. So remember, power function is really what I'm using here. Okay, so review that if you still don't know what I'm doing. So x plus 1 minus 2 lambda, and that gets set equal to 0. So you can solve 3 equations and 3 unknowns. That's why we have the final equation. When you take the derivative with respect to lambda, it just leaves you the cost constraint, which you set to 0 automatically. It forces, well, we made it equal to 0, really, right? We took the function here and solved 70 minus 4x minus 2y equals 0, and we plopped it in the function. So we have 3 equations and 3 unknowns. We can get rid of the lambda, which is customary. And in general, these are all solved in the technical, in the mathematical appendix. The results will always become like this, where this one is, this is just the price on x, and this is the price on y. And the result will always end up being that the marginal benefit with respect to x by the price will equal lambda. That's what you'll get if you solve this. And the marginal benefit with respect to y, divide per dollar, per dollar units, is equal to lambda So what ends up happening, I'm going to move this over. So this just becomes 3 plus y divided by 4 equals lambda, and this one becomes x plus 1 divided by 2 equals lambda. And unless I made a mistake, all you have to do is set these equal to each other. And eliminate lambda. So have a look, let's look through this, make sure there were no mistakes. That will really mess things up. So with respect to x, let's repeat this. That just becomes 3. And treat y as a constant, so that becomes y. And y is a constant, so that becomes 0. And now take the derivative, treat lambda as a constant, just go inside here. And these are all constants, so these become 0. Just leaving the minus 4. So the result here is that the marginal benefit by the price of x is equal to lambda. Marginal benefit of x, or with respect to x, and then below, going through this now for y, so there's no y here, so that's just a constant, becomes 0. There's a y here, so that leaves x. This y becomes 1. And then going through here, the only y is here, leaving negative 2. The rest are just constants. So again, you get this result, the marginal benefit with respect to y over the price of y is equal to lambda. Okay, so we set these equal to each other and put it together with this equation and solve x and y. Then I'm going to cross multiply that up, so it ends up being 3 plus y equals 2x plus 4. Now that is so that y equals 2x plus 1. So that's the result of equation 1. And then I can substitute it in to equation 2. And I'll be able to get x. If I don't make any mistakes. Are you with me? Did I make any mistakes? What happened to this? Nice even number 9. I'm not sure why these things are separating. What's happening? I think my image is breaking down. Okay, so that's 9. So now plug that back into here and find y star is equal to 2 times 9 plus 1, which is 19. So those are my optimal levels. I don't need to solve lambda. I just want to know what the optimal levels of x and y are. Now find the maximum benefit. What's the maximum benefit level? So I have to take those and plug them back into the benefit function to find out. Okay, so this was optimization with a cost constraint. The benefit function was did I do this right? I'm going to remind myself. X was 9 and Y was 19. And that should be the maximum benefit, unless I made a mistake somewhere along the line. Uh-oh, did I make a mistake? I like my answer. Let's go back. How did I get 9? You're right. I like my 9 though. I'm counting too much on feedback. Okay, so 68, that's correct, divided by 8 gives me what? Unless I made a mistake somewhere else. Let me see. I really appreciate you hanging in there, Gerardo. 68. So that leaves me with 8.5, not 9. And then when I put 8.5 in here, I get 18. Very similar answer, but if I was grading myself, I would take 1 point off of 5, maybe, or maybe 1 off of 8 for this problem. Okay. I have 18 and 8.5, so let's do that again. So here I would put all the different numbers. What do you get? All my corrections. So the benefit is 196.5. It was 68 in the second equation, yes. Because I did 70 minus 2 makes 68. I apologize for all the errors. You can't see that very well. Okay, so 196.5. Okay, so I probably stress out a lot of people, but that's basically all you need to know for calculus, how to do those derivatives, right? It becomes simple if you do it enough, but always go back to that sheet, the document that we covered, to remember how to do those derivatives. All right. So it's 10:30. I actually did what I wanted to do, so you should be able to read through the optimization results better or easier or easily. I'm going to share with you the technical solutions so you can practice these problems, the mathematical exercises. Okay, so I'll put that, not send it, but if it's not already in Connect, I'll put it there. I think it was there, but I'll double check. But that's where you're going to find the solutions to these mathematical exercises. So I think I'm going to let you go. Other than that, I'm going to extend the assignment, and and give you more time for it, and I'm also gonna have to post the statistics review for people who need it, who are having problems with chapter 4. Okay? Any questions right now? Thanks for hanging in there, Gerardo. I appreciate you catching my errors. Good night, Mario. Thank you too. Thank you for your questions and your help. Good night.